is an alloy primarily made of iron, carbon, and chromium, which gives it its process of stainless steel begins with the selection of raw materials, primarily sorted and cleaned scrap metal, alongside other alloying elements like nickel, molybdenum, and manganese. The EAF uses electrical energy to generate heat, causing the scrap metal and alloys to melt together into a molten form. Once the initial melting phase is complete, the molten stainless steel undergoes secondary metallurgy. Here, impurities are reduced, and the precise chemical composition of the steel is adjusted. This step is essential to achieving the desired properties, such as corrosion resistance, strength, and hardness, based on the intended application of the stainless steel. Thus, the molten steel is cast into solid shapes through continuous casting. These forms will be further processed into sheets, plates, bars, or wires, depending on the required final product. The next step involves hot rolling, where the steel is heated again and passed through a series of rollers to achieve the desired thickness. For specific applications, stainless steel may also undergo cold rolling, a process that increases strength and enhances surface finish by rolling the steel at room temperature. Final treatments include annealing, which heats the steel to relieve internal stresses, and pickling, where the surface is cleaned using acid to remove any scale or impurities. Stainless steel products may also be polished to improve their surface finish, depending on their intended use. The stainless steel production process ensures that the material is 100% recyclable, which makes it an environmentally sustainable choice. The production of rollers for the steel industry involves a highly advanced and specialized process. The smelting operation is powered by 8 induction furnaces with capacities ranging from 3 to 30 tons, allowing for the production of unit weights up to 130 tons. Modern computer-aided systems calculate the required alloy compositions, which are then transmitted to the furnaces as target values for precise alloying adjustments. Static casting occurs in casting pits for statically cast rolls. Cast parts are formed in casting boxes. The foundry is also responsible for thermal treatments such as annealing to reduce material stresses and optimize the metallurgical properties of the rollers. Rolls are further processed using state-of-the-art equipment across 12 processing halls. These stages include turning, milling, honing, drilling, grinding, hardening, and dynamic balancing, ensuring that every roller meets exacting specifications. For specialized applications like plastic calendar rolls, the facility achieves remarkable precision, with surface roughness below 0.01 micrometers and runout accuracies under 1 micrometer. The processing capacities are substantial, with the ability to handle around 1,500 tons of finished workpieces monthly, producing rollers up to 13 meters in length, 1.7 meters in diameter, and weighing up to 130 tons. This integrated production system guarantees the highest quality and reliability for steel industry rollers. This shaft is intended for industrial applications, drawing on the design of both a reel shaft, used in the coiling and uncoiling of sheet metal, and a generator shaft for energy generation. The process begins with open die forging, where a large block of metal is heated to a high temperature to make it malleable. Open die forging, also known as smith forging, uses flat or simple contoured dies that do not completely enclose the material. In this stage, the heated billet is hammered between 2 flat dies, shaping the shaft while maintaining its structural integrity. After forging, the shaft undergoes sawing to remove any excess material and to cut it down to the correct size for further processing. This step ensures that the shaft has the appropriate length and geometry before moving into subsequent machining stages. Tempering is performed to relieve internal stresses caused by the previous forging and sawing processes. During this phase, the shaft is reheated to a specific temperature below its critical point and then allowed to cool at a controlled rate. This heat treatment improves the shaft's toughness and ductility without compromising its hardness. To ensure the material quality meets stringent industry standards, the shaft undergoes rigorous testing in an in-house laboratory. This involves 2 key tests: notched bar impact test and tensile test. With the material quality confirmed, pre-turning begins. This step involves rough machining the shaft to bring it closer to its final dimensions. Using a lathe, large amounts of material are removed, shaping the shaft into a cylindrical form. Pre-turning allows for faster and more efficient final machining, as the shaft is now prepared for tighter tolerance operations. Milling is conducted to refine the shaft surfaces and to machine key features like grooves, slots, or keyways, depending on the shaft's specific application. Pre-milling removes excess material, while finish milling focuses on achieving precise dimensions and smooth surface finishes. This step is essential for ensuring the shafts fit with other components and its functionality in both coiling, uncoiling, and energy generation systems. The shaft undergoes finish turning to achieve its final dimensions. This is a highly precise operation where minimal material is removed to meet tight tolerances. Once the dimensions are exact, grinding is performed to smoothen the surface to a fine finish. Drilling is employed to create holes or cavities necessary for the shaft's installation or for other functional purposes. Precision is key during this phase, especially in shafts designed for energy generation, where alignment and balance are critical to avoiding performance issues. Non-destructive testing, NDT, is performed to check for any internal or surface defects without damaging the shaft. Two specific methods are used: ultrasonic testing, US testing. Sound waves are transmitted into the shaft, and any reflected signals are analyzed to detect internal flaws, such as cracks or voids. Magnetic particle testing, MP testing. This method uses magnetic fields and iron particles to detect surface and slightly subsurface discontinuities. Both of these tests are essential for ensuring the shaft's integrity and reliability in its final application. Once all manufacturing and testing processes are complete, the shaft is carefully packaged to protect it during transportation. In heavy industry, the process of pattern making, molding, and steel casting plays a critical role in manufacturing large and complex components. These components are often used in industries like shipbuilding, aerospace, construction, and energy, where durability and strength are paramount. The first step in steel casting is creating a pattern. The pattern is essentially a replica of the final product, typically made from wood, metal, or plastic, and is used to create the mold cavity. For large-scale industrial components, patterns must be precisely engineered to account for shrinkage and deformation that may occur during cooling. The design phase also considers factors such as the complexity of the part, the number of units to be produced, and the casting method to be employed. Modern pattern making often integrates CAD, computer-aided design, systems, enabling better accuracy and efficiency in the production process. Once the pattern is ready, it is used to form the mold. In steel casting, sand molding is the most commonly used method, where the pattern is pressed into sand mixed with a binder to form a mold cavity. For large castings, two-part molds or sectional molds are often necessary to handle the scale of the product. The mold is designed with gating systems to direct the flow of molten steel and risers to allow gases to escape and accommodate shrinkage. After the mold is prepared, the pattern is removed, leaving a cavity that mirrors the shape of the final product. The steel casting process begins with steel making, where scrap steel or raw iron is melted in an electric arc furnace or a basic oxygen furnace. Once the steel is melted and refined to the required specifications, it is transferred to the casting section. In the casting stage, molten steel is poured into the pre-prepared mold through a ladle. The metal must be carefully handled to prevent contamination and defects such as porosity or cracks. Once poured, the steel cools and solidifies within the mold. For large castings, controlled cooling processes, such as cooling in a furnace or sandpit, are essential to avoid thermal stresses that could lead to cracks or deformation. After the steel has completely solidified, the mold is broken open to reveal the rough casting. The rough casting undergoes post-casting processes such as fettling, where excess metal from the gating system is removed, and machining, where the casting is precisely shaped and finished. Heat treatments may also be applied to enhance the mechanical properties of the steel, depending on its intended application. The manufacturing of large combustion engines involves intricate processes to produce engines capable of running on liquid or gaseous fuels. These engines, often used in power generation or marine applications, can feature complex components, such as 18-cylinder blocks. Key engine parts, including housings, can weigh over 90 tons when fully assembled, highlighting the scale of these systems. Advanced machining and assembly techniques are crucial to ensure precision and efficiency. CNC machines play a vital role, using data from 3D models and engineering drawings to program exact machining paths. To avoid errors like tool collisions, simulations are conducted prior to manufacturing, ensuring smooth operation. Highly skilled teams, supported by cutting-edge technology, execute these processes with strict quality control at every step. Innovations like toolpath simulations help reduce production time and ensure safety, allowing companies to manufacture engines more quickly and reliably. The manufacturing process at Waldrich Coburg begins with in-house production of all key components, ensuring control over every aspect of manufacturing. From small workpieces to large parts, each element is machined to exacting standards using high-precision machines. For larger components, such as those used in turbines and diesel engines, the company relies on advanced milling, drilling, turning, and grinding technologies. These processes are optimized through automation, including tool changing and spindle exchange systems, which allow for fully automated workflows and increased efficiency. Each machine is fully assembled and tested in their factory before being carefully disassembled for transport to the customer site. This thorough pre-assembly ensures smooth on-site installation and setup. Quality control is integral to the process, with modern measuring and testing equipment used to guarantee the highest precision for each part. Furthermore, the manufacturing process incorporates flexible systems that allow for customization to meet specific customer needs. The deep integration of automation and rigorous quality control ensures that their machines meet the highest industry standards while remaining cost-effective and reliable. The open die forging press operates with a high level of precision thanks to its rigid design with pre-stressed tie rods that ensure structural stability. This high rigidity provides precise guidance for the press, allowing it to deliver the exact forging force required for each operation. The manipulator, used to hold and move the ingot, is programmed to synchronize its movements with the press strokes. Its forward movement, rotation, and lifting capabilities are harmoniously matched with the press, ensuring perfect synchronization during the forging process. This coordination guarantees that the workpiece is consistently positioned correctly, minimizing deviations and enhancing the precision of each forging stroke. In addition to precision, the advanced control systems integrated into the press monitor penetration depth, continuously adjusting the process to maintain accuracy. This ensures that each forging is consistent, with minimal variation from piece to piece, which is especially important when producing components for industries like aerospace and power generation. Another critical advantage of forging technology is the ability to optimize material usage through controlled working allowances. The radial forging machine, with a press force of 16 meganewtons per cylinder, ensures that material is utilized efficiently, reducing waste and saving costs. The process begins with an ingot weighing around 30 metric tons heated to approximately 1,250 degrees Celsius, which is then transported to the forging press for manipulation. During the forging process, the workpiece is initially stretch forged, followed by upsetting to form a gripping neck. This process allows for precise manipulation of the material, reducing the amount of excess material that needs to be trimmed or discarded. The upset workpiece is then reheated and forged again to achieve the desired shape and dimensions, usually first into a square and then into an octagon. This step-by-step forging approach ensures that the material is worked efficiently, minimizing waste and ensuring consistent, high-quality results. Furthermore, the forging press features quick tool change capabilities, allowing for faster retooling between different operations. This feature not only improves productivity but also reduces the downtime typically associated with switching tools, making the production process more streamlined and cost-effective. The final key aspect of forging technology is the assurance of high internal quality. The advanced technology embedded in these presses allows for the creation of a homogeneous microstructure throughout the material, from the surface to the core. This internal quality is vital for producing forgings that meet the demanding standards of industries such as aerospace, shipbuilding, and heavy machinery. During the forging process, the material undergoes several stages of deformation, ensuring that it achieves the necessary mechanical properties. The stretch forging of the gripping neck and the subsequent upsetting and re-stretching processes refine the material's grain structure, resulting in a workpiece with uniform properties throughout. This homogeneity is crucial for components that will be subjected to high stresses in their final applications. In addition, the SMS Mayer Forge-based technology system plays a critical role in maintaining and optimizing internal quality. This system allows forging schedules to be calculated and stored, ensuring that each workpiece is forged according to precise specifications. CNC machining plays a pivotal role in the production of giant crankshafts, particularly those used in marine engines, power plants, and heavy-duty industrial machinery. These crankshafts, often exceeding 10 meters in length and weighing up to 300 tons, require extreme precision and strength to handle the immense forces they encounter during operation. One of the critical advantages of CNC machining in crankshaft production is its ability to achieve micron-level tolerances. For instance, A crankshaft may have tolerances as tight as plus or minus 0.005 millimeters on critical dimensions, such as the main and crankpin journals. These tolerances are essential for ensuring proper oil clearance, minimizing friction, and ensuring the smooth rotation of the crankshaft during engine operation. CNC machining also allows for the efficient machining of complex geometries that are characteristic of large crankshafts. Modern CNC lathes and milling machines can handle intricate features such as oil holes, chamfers, and fillets with high precision. For example, a large crankshaft may require multiple oil holes ranging from 8 mm to 50 mm in diameter, drilled at specific angles and locations along the crankpins to ensure effective lubrication during engine operation. The use of multi-axis CNC machining centers, such as 5-axis or 7-axis machines, allows for simultaneous machining of various crankshaft features in a single setup, significantly reducing production time. For example, turning and milling operations that once required multiple machines and setups can now be done on a single CNC machine, reducing production time by up to 40%. This is especially crucial when dealing with crankshafts that can be up to 1.2 meters in diameter and 10 to 12 meters long. Additionally, CNC technology enhances quality control and consistency in crankshaft production. CNC machines are equipped with advanced measuring systems like laser scanners and touch probes, allowing for in-process measurement and automatic tool compensation to maintain dimensional accuracy throughout production. Gemini's lathes with milling devices are designed to perform a wide range of machining operations with high precision and flexibility, thanks to the integration of multi-process accessories. Their extensive catalog of devices allows users to carry out turning, milling, and drilling processes in one setup, reducing the need for multiple machines and increasing efficiency. The 4-range headstocks provide enhanced versatility and greater chip removal capacity, enabling faster and more precise machining. These lathes are built for reliability and durability, with robust frameworks that ensure consistent performance under the most demanding conditions. Their eco-design reduces environmental impacts throughout the machine's life cycle, from production to disposal, making them environmentally friendly. Ergonomics is a key feature in the design of the lathes, ensuring ease of operation and occupational safety. The machines are developed with the operator in mind, providing a comfortable and efficient workspace. Customization options allow for additional functionalities, such as the integration of smart tailstocks and temperature compensation models, tailored to meet specific customer needs. The lathes also incorporate advanced technologies for smart manufacturing, allowing for enhanced productivity and precision. Modular design further improves finishing capabilities, while the application engineering ensures machines can be specialized to fit any requirement, offering greater rigidity, precision, and user-friendliness. Springs can be made from wire or flat strips and are shaped into various forms, such as coil, tension, compression, and torsion springs. The manufacturing process begins with coiling, where the spring wire is wound into the desired shape. This can be done either cold or hot, depending on the spring's size and material. After coiling, springs are often hardened by heating and cooling them to enhance strength and elasticity. Surface treatments, like shot peening, are sometimes applied to improve durability by reducing surface imperfections. Next, springs undergo grinding to achieve flat and even ends, ensuring proper load distribution. Additional steps, like bending, welding, threading, and assembly, are used based on the spring's final application. Springs are often tested rigorously to meet precise standards, especially for industries such as automotive and aerospace. QNOVA plays a key role in the production of contact tubes for welding tips, a critical component in the welding process. These tubes, typically made of copper due to its excellent thermal and electrical conductivity, are designed to guide the welding wire and transmit the welding current. The process begins with high-quality copper materials that are melted and cast into billets. The billets are then precisely rolled and drawn into the desired tube shape, ensuring uniform wall thickness and durability. After the initial forming, the tubes undergo a series of machining operations to achieve tight dimensional tolerances. This includes drilling the inner diameter to ensure smooth wire feeding and minimal friction. Surface treatments, such as plating or coating, may also be applied to enhance the wear resistance of the tubes, especially under high thermal loads during welding. The production process is highly automated and overseen by experienced engineers, ensuring consistency and high quality. The company's focus on innovation allows it to adapt its contact tubes to the evolving needs of the welding industry. A hydraulic open die forging press is a fully hydraulic controlled piece of equipment designed to transfer energy through hydraulic pressure for forging metals such as alloy steel, stainless steel, and high alloy steel. The press is widely utilized in the production of high forging depth capability, allowing it to shape larger and thicker materials efficiently. High rigidity, allowing the press to handle heavy loads and resist deformation under pressure. PLC, Programmable Logic Controller, providing precise, automated control of the forging process, ensuring accuracy and repeatability. A reliable electrical cooling system, preventing overheating and ensuring the press can operate for extended periods without loss of efficiency. This combination of features makes the hydraulic open die forging press an essential tool for producing large, high-quality forgings across various industries. The film highlights the production process of a heavy steel block, an exhibit showcased by Shewin AG at the Euro BLECH trade fair in Hanover. This block is a solid steel piece